Hello, everyone. Sorry I couldn't make it today. I wish I could be there, but instead I have this nice video lesson for you. Hopefully you can follow along on your self-paced Neuropod. You found that okay on Canvas. So here are our learning targets. Let me give you a moment to read your learning targets. Okay. So I will learn to prove the hypotenuse leg congruency theorem. I will learn to analyze and see where to use side, 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 angle, and or angle, angle, side, triangle congruency to justify the leg congruency theorem and the leg angle congruency theorem. You know you're successful in this lesson if I can apply right triangle congruency theorems to solve problems. So we're going to dig into right triangle congruency theorems. I'm going to show why they work. It's just one of many congruency theorems that we're going to use this quarter, and let's go forward. Let's go forward. So if you're following along in your book, go ahead and flip it to this chapter: side, 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 angle, angle, side, SOS. Using triangle congruency to determine relationships between segments. And what I'm going to do is I'm going to flip back and forth through this Neuropod and the .cam. We're going to work out a few of these, but let's start out with a poll. So the interior angles of a triangle add up to 180 degrees. Hopefully we know that one right now. Hopefully we're good on that one. Let's move on to the next poll. For triangles to be a right triangle, then it has to have one 90-degree angle. At least one angle that's 90-degree angles. And the last poll. Which of the following is the Pythagorean theorem? So A is actually area of a triangle. B, C, and D are congruency theorems that I think we all know. And of course, E, lastly, is the Pythagorean theorem. So in this next slide, what I'd like you to do is go ahead and label the sides in the following triangle: leg and hypotenuse. So which ones are the legs, which ones are the hypotenuse? And then after that, write out the Pythagorean theorem using the numbers in the triangle. So what I'm going to do is give you a little bit of time on this slide. Then we'll come back to this. All right. Thank you for coming back. What I'm going to do is I'm going to switch over to my .cam and go over this particular problem, and let's see where we're at. Actually, .cam's next. Here we go. So we're going to label the sides in the following triangle: leg and hypotenuse. Which ones are the legs? Well, let's start with the hypotenuse instead of legs. So the hypotenuse is always that side that is directly across the 90-degree angle. So this would be our hypotenuse. Our legs are going to be the other two sides. This one here I would call the short leg. B, C, I would actually call the long leg. Doesn't necessarily, they're not always going to have a short leg. They're not always going to have a long leg. They may both have the same size leg. That's okay. But make sure you recognize the legs and the hypotenuse and how to find the hypotenuse. That part is critical. And the Pythagorean theorem states that if we take a leg and we square it, we take another leg and we square it, it'll equal the hypotenuse square. Doesn't matter if you mix up these two legs. It matters if you mix up the hypotenuse in this example. So using the numbers in this particular example, how would you set up a problem like this? It's going to be 5 square plus 12 square equals 13 square. So we're setting up that problem. It depends on what we need to find. The Pythagorean theorem will help us find either one of these legs or the hypotenuse, just using a little bit of algebra. All right, let's go back to our neuropod. So the next slide in neuropod is going to deal with these two triangles. The first triangle is what the one that we're just on. See if you can apply the Pythagorean theorem to both of these triangles. I'm going to give you a little bit of time to do that, and then pause this video. We'll come back. We'll work these problems out. All right, welcome back. Let's go into the DocCam. And DocCam is going to be a little laggy. It usually is, but bear with me. So in this particular problem, we know the values of the legs. We have a leg here, we have a leg here, and we have our hypotenuse right here. The way I know that's the hypotenuse is because it is directly opposite of the 90-degree angles. So we're going to go ahead and set this up. We got 5 square plus 12 square equals c square. Before I begin to do anything in this particular process, what I'm going to do is I'm going to go ahead and unsquare my legs. So that's going to give me 25 plus 144 equals c square. Combine our like terms, it's going to be 169 equals c square. And at this point, we're solving for c. We want to know the hypotenuse of this particular problem. So we're going to unsquare this c. And the way you do that is you square root both sides of the equation. The square root of 169 happens to be 13. And an unsquared c, so this is symmetric. We can go ahead and write it like this if we wanted to. So the hypotenuse equals 13. Let's look at the second one. A little bit different, isn't it? First problem, we're looking at the legs and trying to find the hypotenuse. This problem, we have the hypotenuse, we have one of the legs, but we're missing one of the legs. We can still set the problem up the same way and use a little bit of algebra to find out what we're looking for. So let's go ahead and call this A. So I have a squared plus 6.6 squared. Notice how I put that in parentheses, equals 10 squared. So I need to find this leg. I'm going to go ahead and isolate this variable. I'm going to subtract 6.6 squared from both sides. The reason why I put these in parentheses is I do not want to confuse what's being squared. I'm squaring the entire number, not part of the number. So that leaves us with a squared equals 10 squared minus parentheses 6.6 squared. Don't hesitate to use a calculator in a problem like this. We're going to go ahead and unsquare. Leaves us with a squared equals 100 minus, I'm not exactly sure on the top of my head what 6.6 squared is. So let's go ahead and raise it to the power 2. That's 43.56. So we got 100 minus 43.56. And that leaves me with a squared equals 56.44. Solving for a, let's square root both sides. That's just going to leave me with a. And the square root button on your calculator is, don't forget to hit the second. It's going to take you to these blue lettered inputs on the top of the buttons. 56.44. And highly recommend that you close off the parentheses when you're working with a calculator like this. That way the calculator doesn't get confused. So that leaves me with a pretty long decimal. Let's go ahead and round it off to the nearest tenth in this particular problem. So if I look at the 1, so I'm just going to leave it at 7.5. So in this particular case, A equals 7.5. All right. Don't hesitate to go back and rework this if you didn't quite understand the process. Let's go back into the Neurapod. So here's some key terms I need you to have and look for them in this lesson. Hypotenuse leg congruency theorem, leg-leg congruency theorem, leg angle congruency theorem. We're going to work on those in this upcoming lesson. Maybe not completely get to this today, but expect to see it in the next couple of days, the next couple of lessons. So the hypotenuse leg congruency theorem. So let me read this out to you. Many congruency theorems apply to all right triangles. There are also theorems that apply only to right triangles. If you have already proven the hypotenuse angle congruency theorem, methods for proving that two right triangles are congruent somewhat shorter. All right, so let me repeat this. Many congruency theorems apply to all right triangles. There are also theorems that apply only to right triangles. You have already proved hypotenuse. Hold on here. So many congruency theorems apply to all right triangles. There are also theorems that apply only to right triangles. So we haven't really dug into hypotenuse angle congruency theorem, so I'm going to go ahead and skip that part. But methods for proving that two right triangles are congruent are somewhat shorter. You can prove that two right triangles are congruent using only two measures. So if you might remember, with the side-side-side congruency theorem, we were looking at three congruent sides. With the side angle side, we were looking at two congruent sides and an angle. And then with angle side angle, we were looking at two congruent angles and a side. So those were three pieces that we were looking at, and to see if both those pieces corresponded with the other triangle, and if they matched, then we can go ahead and say that they are congruent.
Again, remember to exit out the door you lectured, and please return your laptop. But mostly, have a wonderful afternoon.
Gotta love dismissals, right? Let's move on. Look at this proof. Pause the video, look over this proof before we go on to the next slide. Let's try to work this proof. Okay, let's go into that slide. And we'll come back to it. So let's go ahead and go into the .cam. How did you do? How did you fare on this? Hopefully you tried it out, then throw your hands up, but let's see how these proofs work. This will be a proof to expect to see on the next upcoming test. So I want to make sure that you clearly understand how to go about it. So let's get into that .cam. So what do we know? So we have the right triangle ABC with right angle C, right triangle DEF with right angle F. AC is congruent with DF, AB is congruent with DE. And we need to prove that triangle ABC is congruent to triangle DEF. If you don't remember, I'm going to stress it one more time. Make sure you mark up your triangle if it's not already marked up, and if it is marked up, double check. So what does it mean that right triangle ABC with right angle C? What does that mean? Well, that this angle right here is a 90-degree angle. And that right triangle DEF with right angle F, what does that mean? Well, is that's right. It's very important. AC is congruent with DF. AB is congruent with DE. There we go. So looking at what we have so far, can we use any of our theorems? Can we use side, angle, side, or angle, side, angle? Can we use any of those? Or even, just in case you've gotten that far in math yet, angle, side, can we use any of those? At this point, we can't. Because if I look at it, this is side, angle, side, angle. It's not going to work. So we need to prove that CB is congruent to FE. And the way we're going to do that is we're going to use the Pythagorean theorem. Let's go through this process. We have our list of statements, and then we have to figure out why can we say these things. For A, that's the easiest part. They're given. Right? For C, angle C is congruent to angle F. C and F. Well, if I look over here, that's right angle congruency postulate. So that's one to write down here. I'm going to abbreviate a little bit. All right, so we got that one out of the way. And if you want, just for the process, just check it off. AC is congruent to DF. AB is congruent to DE. Well, that's our given again. And notice what's changed. We went from a congruent symbol to an equal symbol. Whenever we see that, we're talking about the measures of those segments. So it's going to be the definition of congruent segments. My O's look like U's. I know. What happened here with E? What did they do? It looks like they squared both sides. So squaring both sides. What's changed here? The only thing that's changed is now we have an addition going on here. We have something that's being added in here. A piece that wasn't once there. In our case here, CB is added in, FE is added in, but everything else is set up. And it looks to me that the author of this proof is using the Pythagorean theorem. All right, and this next one, what changed between the two? What changed? Well, we used some substitution. That's what's changed. It's different up here. If you look up here and you look here, we're just replacing some pieces here. We're just replacing some pieces. So I'm going to go ahead and say substitution property. What changed from here to here? So we just have CB and FE, and in reality, those are the points that we need to show that all three sides are congruent. And if all three sides are congruent, we can go ahead and use this side congruency theorem if we wanted to. We can also use side angle side, but we used that Pythagorean theorem for that to happen. what changed? So what changed was that we subtracted AC and FE. How can we get away with subtracting that? It's from up here. It's from up here. It's where it's from. We're saying that they're the same thing. So AC and DF, sorry, not FE. AC and DF. We're saying that AC and DF are equal. If they're equal, they're the same numbers, like subtracting 1 and 1, 2 and 2. So those were subtracted. So that's what we're going to write down here. Subtraction property. I know over here they say something else. They use algebra, but it's more than just algebra. All right, here, what's changed? Well, it looks like the only way that we can go from a squared segment to an unsquared segment is if we square rooted both sides. And then notice how we go from an equal to a congruent. That is our definition of congruent segments. And then lastly, why can we say that triangle ABC is congruent to DEF? Well, what we just did in this proof is we showed that CB is congruent to FE. That was the final piece that we needed to show that these triangles were congruent. And we can say they're congruent because they're side, 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 or they're congruent because they're side, angle, side, because we do have side, angle, side. So it's going to be this one here. Since I was aiming for side, side, side the whole time, I'm going to write that down in that final column. All right. Try this out again. See if you can go back into that Neuropod, make some adjustments if you want, and try to repeat that part. All right, so that's all I have. If you have any questions, don't hesitate to email me. Drop by office hours on Tuesday, Thursday, and Friday. I'll be able to help you out. Other than that, have a great weekend.